Okay, perhaps let us start. Can you go to the title? Yes.
Sure. Yes.
Okay, welcome everybody to this week's Marana Raichaudhuri seminar series. Our first speaker is Dr. Dhrubajyoti Gogoi from Dibrugarh University, and he is going to talk about some properties of gravitational wave in modified theories of gravity.
Okay. Thank you. So this is my presentation overview. So at first I will talk about the theory of gravitational waves in brief, and then I will talk about some modified theories of gravitational waves, and then I will particularly focus on two particular properties of gravitational waves. One is the polarization mode of gravitational waves, and the other one is quasi-normal mode of gravitational waves. So so as you know, this is the gravitational action given by equation 1, and the field equation is given by equation 2, which is known as the general Einstein's field equation, where this capital J mu nu represents Einstein's tensor, and this T mu nu represents energy momentum tensor. And the explicit form of this capital G mu nu is given by this expression, where this R mu nu is the Ricci tensor and this R is Ricci scalar. Now, if we would like to see the effect of gravitation waves theoretically, then what we do, we introduce a perturbation, small perturbation is mu nu to the background, and in presence of this perturbation, we derive the expressions for Ricci tensor, Ricci scalar, etc. And at far distance away from actual source of gravitational waves, the field equation reduces to this particular form, the part of field equation, which is given by equation 6. Now this equation 6 tells us that there is no massive polarization modes of gravitational waves in general theory of relativity. There are only two degrees of freedom present in general theory of relativity, and therefore we have only two polarization modes, which are known as tensor plus and tensor cross polarization modes, which are shown here in this figure. So this one is tensor plus polarization mode, and this one is tensor cross polarization mode. And since there is no scalar propagation mode present in general theory of relativity, hence gravitational waves propagate with the speed of light through the space-time. Now, this is the first source of gravitational waves that was detected by LIGO Observatory. So, the significant sources of gravitational waves are supermassive binary black holes, neutron star mergers, or black hole neutron star mergers, etc. Now, before going to modified theories of gravity, let me briefly talk about some limitations of general theory of relativity. All the limitations of general theory of relativity can be mainly classified into two categories. One is the observational limitation, which says that general theory of relativity disagrees with an increasing number of observational data at the infrared scales, and those are mainly accelerated expansion of universe, galactic rotation curve, gravitational lensing, etc. And the other one is a kind of theoretical problem, which states that the theory cannot be renormalizable and cannot be quantized at the UV scale. Now, I will move to modified theories of gravity. So, since we have seen that there are several limitations of general theory of relativity, so we can remove these limitations by simply modifying the field equation of general theory of relativity in a meaningful way. So, what are the ways in which we can modify general theory of relativity? So, I will include just a few things here. So, we have two options mainly. Either we can go for modifying the geometry part of this field equation on left hand side, or we can modify the energy momentum term on the right hand side. So if we modify the geometry part, then we end up with different kind of higher order gravity, Russell gravity, FR gravity, FRT gravity, etc. Or if we modify the energy momentum term, then we can obtain different kind of dark matter dark energy models. And this is the simplest extension of general relativity, as you know, which is known as the lambda cold dark matter model. And in the different modified theories of gravity, as we have found from the literature, we have seen that in depending on the type of modified theories of gravity, we may observe different numbers of polarization modes of gravitational waves at very far distance away from actual source of gravitational waves. And in defined metric theories of gravity, due to the presence of higher order curvature term, there may be a longitudinal polarization mode present, and this results a variation in the propagation speed of gravitational waves. And we have also seen that uh, different types of complex stars, for example, strange star, neutron star, etc., can be studied in different modified theories of gravity, and we have seen that a significant variation in the structural configuration has been observed till now. And the gravitational wave power spectrum also changes in different modified theories of gravity depending on the type of modification introduced to it. And we have also seen that the black hole solutions are significantly affected in different types of modified theories of gravity, and therefore the quasi-normal modes from black hole solution or black hole spacetimes also get changed. And apart from these changes, there may be a lot of other changes which are yet to be explored. So now I will briefly discuss about polarization modes of gravitational waves in a type of modified theories of gravity, which is commonly known as FR gravity, which is a very common modified theories of gravity. So the story basically started with Korda, who for the first time studied the propagation of gravitational waves in FR gravity, and then several people applied Newman-Penrose formalism to FR gravity in order to investigate the number of polarization modes. In 2016, Hafiza Rizwana Kausar and her team published a paper in PRD, and they reported the presence of four polarization modes of gravitational waves in FR gravity metric formalism. However, in the same year, Myung published another paper which says that there is only 3 degrees of freedom present in FR gravity metric formalism, and therefore we cannot have four explicit polarization modes of gravitational waves. And later in 2017, Dikong Liang and his team published another paper in PRD which confirms the results obtained by Myung, and they also confirmed that yes, there are only three polarization modes of gravitational waves in FR gravity metric formalism. So what they found is that the third polarization mode, that is the scalar polarization mode, is basically a mixture of massless breathing mode and massive longitudinal mode. And this scalar mode basically propagates slowly in comparison to the tensor polarization modes. So for testing their investigation, we started our study by simply considering a very basic FR gravity model, which is known as the power law model, and we obtained a part of field equation around a d theta curvature, and we have found that the field equation is stable only for a particular value of the model parameter n, and that is n equal to 2. And for n equal to 2, by introducing transverse stressless gauge condition, we have found that there are three polarization modes of gravitational waves present in FR gravity power law model. But interestingly, the third polarization mode in FR gravity power law model is massless in nature. And to confirm this result, we also considered the scalar tensor theory equivalence of FR gravity power law model, and we obtained basically this solution of gravitational waves from the part of field equation given by equation 16, where this first part represents the tensor standard tensor polarization modes, tensor plus and tensor cross polarization modes, and this part represents massless breathing mode, which is a scalar polarization mode, which is transverse but not traceless. And here, to obtain the solution, we have considered that the gravitational wave is propagating along z-axis. So we also investigated the geodesic deviation equations in order to confirm the results, and these equations also confirm the presence of a massless breathing mode in the theory. So what we have found is that the polarization modes in FR gravity metric formalism are basically model dependent. For different types of FR gravity model, we may obtain different types of different behavior of polarization modes. And for pure R square model, we have found that there are three polarization modes of gravitational waves, and gravitational wave is massless in nature. So technically speaking, it is the only FR gravity metric FR gravity model in which we can obtain massless gravitational waves spontaneously. And then what we did, we introduced another FR gravity model apart from the existing ones to investigate the behaviors of gravitational waves. The motivation behind introducing this FR gravity model is that although we have a lot of FR gravity models, those FR gravity models suffer from several issues. They have a lot of limitations. If investigate the limitations of different Afra gravity models, and by investigating the limitations of different
Hello?
Afra gravity models. Yes.
Sorry, your screen is, we cannot see your screen.
Yeah. Am I audible?
Yes.
Yes. So should I continue?
But we cannot see your screen. Can you start the screen share?
Okay. Sure. Uh, can you see my screen now?
Yes.
Okay. Okay, so this is the Afra gravity model that we have introduced, and this Afra gravity model has three model parameters: alpha, beta, and RC. Alpha and beta are two model parameters which are very small, dimensionless positive constants, and RC is a characteristic curvature constant. So you can see that this model has two correction terms, this term, and this model satisfies all the five necessary conditions for a valid dark energy Afra gravity model. So we investigated this model in Jordan frame and in Einstein frame, and obtained the expressions for mass square and potential, and plotted them here. So this is the behavior of mass square with respect to the background curvature, and this is the variation of potential with respect to the background curvature. And we also investigated the same model in Einstein's frame, and we have seen that the qualitative behavior of mass square and potential is are identical. Okay, then we investigated the model in the solar system, and by implementing the solar system test functions, we have seen that the model behaves quite fair in the solar system regime, and it passes all the solar system test functions properly. So that is why this model is also capable of explaining perihelic precision and everything that is happening inside our solar system also. And after that, we considered our Afra gravity model along with Stravinsky model and Husaki model, which are two very feasible Afra gravity models, and tried to investigate the stability conditions by considering a stable de Sitter solution. And for these two models, what we did is that we investigated the stability region for our model, and here for Stravinsky model, and for Husaki model, and we have found that our model has larger stable model parameter space. And then we also investigated the observational feasibility of this model, and by considering the gravitational wave data and AVEL 1689, AVEL 1991, and AVEL 383 data, we have constrained the model, and we have seen that the model passes the observational constraints put by gravitational wave data and AVEL data, galaxy cluster data. So this is the constraint on the model from gravitational wave event 170817, and this is the constraint on the model parameter alpha. Now, in order to investigate the polarization modes of gravitational wave in this model, we proceed in the same way and obtain the part of field equations. And this equation for 2 basically represents the standard tensor polarization modes. And in order to confirm the existence of scalar polarization mode, basically we can rely on this equation 38, which basically says the existence of or predicts the existence of massive scalar mode. However, we cannot explicitly say whether the scalar polarization mode is a mixture of longitudinal mode and breathing mode or not. So in order to confirm the existence of massless breathing mode, we rely on the Newman-Penrose formalism. However, this Newman-Penrose formalism is basically applicable to null waves only, or massless gravitational waves only, and that is why what we can conclude from this is that the results obtained by Kausar or other authors were not very accurate, and this was also shown by Liang in their paper. And therefore Hyun in 2019 published another paper in PRD, which basically modified the existing Newman-Penrose formalism, and they tried to calculate the explicit Newman-Penrose quantities, and by calculating the explicit Newman-Penrose quantities for a massive metric theory, they calculate the polarization modes. However, what we have found is that their modification was not very accurate, and that is why this model or this modified Newman-Penrose quantities cannot simply predict the existence of a massless breathing mode, and that is why we further modified the standard Newman-Penrose formalism, and we obtain these four Newman-Penrose quantities, which basically says the existence of standard tensor polarization modes by psi4, existence of a massive longitudinal mode by psi3, and psi2 and psi3 equal to 0 says that there is no vector polarization modes present in this theory, and phi22 basically represents massless breathing mode. We also considered some selected data of pulsar timing arrays, and we have found that although the pulsar timing array data cannot simply constrain the model parameters properly, but it does not nullify the existence of a massive polarization mode in the theory. And to confirm the results associated with massive polarization mode, we have to wait for LISA, or we have to wait for under 5 or 10 years, so that we can have a larger data set associated with pulsar timing arrays, which can effectively constrain the model parameters. So these are the conclusions from this result. And now I will briefly talk about quasi-normal modes. So because by simply observing the polarization modes, we cannot effectively constrain a modified gravity model, and that is why we have to rely on quasi-normal mode data also, because the quasi-normal modes are basically closely related with the black hole space-time, and the black hole space-time is again closely related with the modified theories of gravity, and any modification to the theory significantly impacts the black hole space-time. So that is why we expect that by simply observing or constraining the quasi-normal mode data, we can constrain a modified theories of gravity. So for this purpose, here in this presentation, I have chosen bumblebee gravity. So this is the Lagrangian associated with the bumblebee gravity. So this basically here in this theory, we introduce a vector field which non-vanishing vacuum expectation value, and due to the presence of this vector field, the standard Lorentz symmetry is violated, and the associated field equations are given by these equations 50, 51, 52, and 53, and by solving these field equations, we obtain a line element given by equation 56, which represents a black hole solution. Now what we have found here is that in bumblebee gravity, due to the presence of Lorentz symmetry violation, and since it is a standard model extension theory, we have to introduce other two parameters, and one parameter is basically associated with global monopole. Since this is a standard model extension theory, we have to introduce a global monopole in order to obtain some feasible results, and apart from this, in order to introduce quantum corrections, we have to introduce generalized uncertainty principle to the theory, and by using generalized uncertainty principle and by introducing a global monopole, we have obtained a modified black hole solution, which is basically given by this equation 62, and in this equation 62, mgup basically represents the GOP modified mass of the black hole, and this mu basically represents a global monopole term. So in presence of cosmological constant, so these are the metric functions associated with the black hole space-time in bumblebee gravity, and these are the expressions of event horizon radius and metric functions for GOP character anti-de black hole, and this is the expression for mass. And similarly, we obtained the GOP character de black hole solution. So I'll skip this part. And then we considered three types of perturbation here in order to investigate the quasi-normal modes. So we consider scalar perturbation, and this is the potential associated with the scalar perturbation. L is the multiple moment, and this is the potential associated with this is basically potential associated with electromagnetic perturbation. So this is basically a typo. So this is the potential associated with gravitational perturbation, and these are the results associated with quasi-normal modes. So here we have utilized sixth order WKB approximation method, sixth order Pade-Everest WKB approximation method, and time domain analysis in order to obtain the numerical values of quasi-normal modes. So basically from this table you can see that the quasi-normal modes are nothing but some complex numbers, where this real part represents the oscillation frequency of gravitational waves, and this imaginary part basically represents the damping rate of gravitational waves. And we have calculated these quasi-normal modes for n equal to 0. So for different values of L, you can see that the oscillation frequency of gravitational waves increases significantly, and there is no significant variation in the damping rate of gravitational wave. So these are the error terms associated with the numerical calculations associated with the WKB approximation method. So this term, basically this column, represents error associated with the sixth order WKB approximation method, and these are RMS errors. And this basically represents the errors associated with the Pede-Everest sixth order WKB approximation method, and this R square basically represents the fitting behavior of quasi-normal modes obtained from the time domain profiles. So similarly, we have obtained quasi-normal modes for electromagnetic perturbation also and gravitational perturbation also, and then we compared our quasi-normal mode data with the quasi-normal mode data obtained by some other investigations for a standard Schwarzschild black hole with GOP corrections, and for black hole solution in Bumblebee theory. And then we plotted the variations of quasi-normal modes with respect to the model parameters. So this is the variation of oscillation frequency of gravitational waves with respect to the model parameter alpha, and this is the variation of imaginary quasi-normal mode, that is the damping rate, with respect to alpha. Here one can note that the absolute value of omega I, that means the imaginary part of quasi-normal mode, represents the damping rate, and that means that this variation implies that with an increase in the model parameter alpha, the damping rate of gravitational wave increases. So this is the variation of oscillation frequencies of gravitational waves with the Lorentz violation term lambda, and this is the variation of damping rate with Lorentz violation term, and this is the variations of quasi-normal modes with the global monopole term mu. And these are the variations of quasi-normal modes with respect to the model parameters for the d Sitter black hole and for the anti-d Sitter black hole. And these are the variations of quasi-normal modes with the effective cosmological constant in the Bumblebee gravity theory. And here I have shown the calculations associated with the time domain profiles for investigating the evolution of scalar electromagnetic and gravitational perturbations. And these are the time domain profiles associated with the scalar electromagnetic and gravitational quasi-normal modes, and these are the time domain profiles of quasi-normal modes for the scalar quasi-normal modes, scalar perturbation for defined multiple moments. And this is the implementation of Levenberg-Marquardt algorithm that we have utilized in order to extract the quasi-normal modes from the time domain profiles. And then we also considered some detection possibilities of quasi-normal modes, and by considering these possibilities, we have found that even if the black hole is of the size of Sagittarius A, our ground-based gravitational wave detectors, for example LIGO and Virgo, will not be able to detect the quasi-normal modes, and we have to wait for LISA, which has a higher sensitivity range, in order to detect the quasi-normal modes properly, and only then we'll be able to constant the model parameters associated with defined modified theories of gravity effectively. And then we considered sparsity of Hawking emission in this theory also, so I will skip this part for now. And we also investigated the power spectrum of gravitational waves for defined model parameters, and we also found that the sparsity of the black hole does not significantly depend on the model parameters in Bumblebee gravity. And this is the brief summary of this work. And what we have found here is that the quasi-normal mode spectra is significantly impacted by the GOP parameters, Lorentz violation parameter, and the global monopole parameter. And then here we have investigated the quasi-normal modes from wormholes in gravity. So I'll just qualitatively go through this part. So here we have considered three toy shape functions of wormholes, And these are the representations of structure and stability of the wormhole toy shape functions. This is just function 1, this is for function 2, and this is for function 3. And apart from this, we have also considered Fragravity Starobinsky model along with a cloud of strings and obtained a shape function which is given by equation 105. And then we studied the stability of this wormhole, and finally we consider scalar perturbation and Dirac perturbation in order to obtain the quasi-normal modes from wormhole spacetimes. And here we have implemented third order WKB approximation method and fifth order WKB approximation method in order to obtain the quasi-normal modes. And here for scalar perturbation, you can see that the errors associated with the third order WKB approximation method is higher here, and the errors associated with the fifth order WKB approximation method is less. However, in case of Dirac perturbation, if you observe that here the third order WKB approximation method seems to be more efficient in comparison to the fifth order WKB approximation method. And these are the variations of quasi-normal modes with respect to the model parameters of the wormholes. So I'll just keep it for now. And this is the time domain profile for the wormhole represented by equation 105 for the Starobinsky model. And we have also considered connecting quasi-normal modes along with the shadow of a black hole so that we can constant the model parameters more effectively. And this is a analytical relation connecting the imaginary and real part of quasi-normal modes along with the shadow radius of a black hole, where this capital RS represents shadow radius of the black hole. So we have also considered thermal fluctuations and different types of quantum corrections, and tried to study the impacts of black hole thermodynamics. And we are also trying to relate the black hole thermodynamics along with the quasi-normal mode spectra so that we can simply study or investigate the behaviors or variations of black hole thermodynamics and quasi-normal modes parallelly. So this is the summary and conclusion of my presentation. So what we have seen from my presentation is that for different types of modified theories of gravity, we can observe different types of polarization modes at very far distance away from the actual source of gravitational waves. And basically in metric FR gravity theory, we obtain massive polarization mode. However, if you consider Pellatini FR gravity model or any type of Pellatini FR gravity models, you will not see additional polarization mode. There will be only two polarization modes, tensor plus and tensor cross polarization modes. And we have also seen that the standard Newman-Penrose formalism cannot be applied to FR gravity in metric formalism due to the presence of massive gravitational waves or massive polarization modes. And that is why we have introduced a modified version of Newman-Penrose formalism, which is capable of distinguishing the massless breathing mode of polarization mode of gravitational waves. And apart from this, we have also considered quasi-normal modes for different modified theories of gravity. Here I am just showing a few results only, and we have seen that for different types of modified theories of gravity, the quasi-normal mode spectra is significantly different, and that is why in the near future, with significant observational data from LISA, it might be possible for us to constant different modified theories of gravity in terms of quasi-normal mode data. And there are some these are